Dirac Delta function. In the mechanical systems, electrical circuits, bending over beams and over applications, one encounters functions that have very large value over a very short interval. For example, the strike of a hammer exerts a relatively large force over a relatively short time. Heavy weight concentrated at a spot on the suspended beam exerts a large force over a very small section of a beam. To deal with the violent forces of short duration, physicists and engineers use the delta function introduced by Paul Dirac. We introduced approximation to Dirac function, so we want to fix a point t equals to t null, and at this point we want to have infinity. We cannot have infinity immediately, so what we do is we say function equals to 0 outside of small interval, and that small interval will have t null minus a on the left and t null plus a on the right. And in that interval, value of function is big, and say value of function on that interval is going to be equal to 1 over 2a. So eventually, when interval getting smaller and smaller, value of function is going to be shooting bigger and bigger, then a becomes 0, value of function will be infinity. So that is our approximation for Dirac delta function. So delta a over t minus t null equals to 0 if t is less than t0 minus a. And usually we assume that we start at 0. 1 over 2a on the given interval, t null minus a, t null plus a, and 0 when t is bigger or equal than t null plus a. And we define Dirac delta function to be Dirac delta function at the point t null, limit of our approximation when a is approaching 0 of delta a t minus t null. So delta function at t minus t null equals to infinity when t equals to a given point t null and 0 otherwise. Also, we can notice the property that integral from 0 to infinity of our approximations equals to 1, and therefore integral of delta function, which is limit of our approximations, is also going to be equal to 1, or in general at t minus t null it's going to be 1. Now, if we want to find Laplace of delta function at t minus t0, we claim it equals to negative st now. Let's see how we can try to prove it. Firstly, we try to find approximation to delta function at t minus t null. So that is, we can rewrite it using step functions, using window function as u of t minus t0 minus a, step function at the left point minus step function at the right point, t0 plus a. Now we take Laplace of approximation, delta a. We're going to get 1 over 2a. Laplace of step function we are familiar with, so it's e to the negative s t0 minus a over s minus e to the negative s t0 plus a over s. Now to find Laplace of delta function, we take limit of our approximation when a is approaching 0. So we're taking limit as a approaching 0 of the expression we just derived. I'm going to write that expression as one big fraction, e to a negative s t0 minus a minus e to a negative s t0 plus a. I'm going to rewrite that expression as 2as e to a negative s t0, going to distribute s inside, so I'm going to get sa minus e to a negative s t0 minus sa. So I can factor e to the negative s t0 out. I'm going to get e to sa minus e to the negative sa over 2as, and I want to take limit to that expression when a is approaching 0. If I'm substituting 0 for a, I'm going to get 1 minus 1 on top, 0, 0 for a, 0 in the denominator, so I can use L'Hopital rule. And if I use L'Hopital rule, taking derivative with respect to a, I'm going to get 2s in the denominator. E to the negative s t0 is a constant with respect to a. Derivative of e to the negative e to the sa becomes s e to the sa. Similar way, it will be plus e to the negative sa times s. Limit when a is approaching 0. Now substituting 0 for a, we're going to have 2s on the bottom. We're going to get e to s t0 on top, s plus s. S plus s is 2s, and that's exactly what we wanted to have. As a corollary from that statement, what we can do is, if we want to get Laplace transform of just delta function, when t0 equals to 0, we're going to get just 1. So Laplace transform of delta function is 1. If we want to do the following differential equation, second derivative plus y equals to 4 delta function at t minus 2 pi. We'll do two examples, A and B. In the first example, my initial condition will be y of 0 equals to 1 and y prime of 0 equals to 0. I'll take Laplace transform of both sides, so I'm going to get Laplace of y second plus Laplace of y equals to Laplace of 4 delta at t minus 2 pi. Laplace of y double prime equals to s squared Laplace of y minus sy of 0 minus y prime at 0 plus Laplace of y. 4 as a constant can be taken out. We already found Laplace of delta function, so it's going to be e to a negative 2 pi s. Using the initial conditions, y of 0 is 1, y prime of 0 is 0, we're going to get s squared Laplace of y minus s plus Laplace of y equals 4 e to a negative 2 pi s. So Laplace of y times s squared plus 1 equals to s plus 4 e to the negative 2 pi s. So Laplace of y is going to be s over s squared plus 1 plus 4 e to the negative 2 pi s over s squared plus 1. y equals Laplace inverse of this one is cosine plus 4 e to the negative 2 pi s means we need to put step function 1 over s squared plus 1 Laplace inverse is going to be sine, because we need to switch it to t minus 2 pi, so we're going to get sine of t minus 2 pi. Notice that that expression eventually is going to be just sine of t. So finally we have our answer, y equals cosine of t plus 4 sine of t u of t minus 2 pi. So what is happening, if you want to kind of get an idea what is going on here, is we have our function which behaves like a cosine, and then at 2 pi we have that new function also comes into play, and then we have immediate jump and it starts behaving slightly different. So that's where we have effect of that Dirac function, delta function. So if you like, we also can write our answer in by cases. So it equals to cosine till t less than 2 pi, and then it equals to cosine of t plus 4 sine of t, then t is greater or equal to 2 pi. Here we do the previous example with different initial conditions, so we still have second derivative plus y equals to 4 delta function t minus 2 pi, and now we do different initial conditions and we say y of 0 equals to 0 and y prime of 0 equals to 0. We'll repeat our calculations, the same which we did in the previous steps. Laplace of y double prime plus Laplace of y equals to Laplace of 4 delta at t minus 2 pi. So we're going to get s squared Laplace of y minus s y of 0 minus y prime of 0 plus Laplace of y equals to 4 e to the negative 2 pi s. Y of 0 is 0, y prime of 0 is 0, so we're going to get Laplace of y times s squared plus 1 equals to 4e to the negative 2 pi s. So we're going to get Laplace of y equals 4e to the negative 2 pi s over s squared plus 1. Taking Laplace inverse of both sides, we're going to get y equals 4 sine of t minus 2 pi step function at t minus 2 pi. So y equals 4 sine of t times step function at t minus 2 pi. So if rewrite that answer in function defined by cases, it equals to 0 till t is less or equal than 2 pi, and after that it equals to 4 sine of t when t is bigger than 2 pi. And if you like, we can draw that on a picture, this function. So function equals to 0 till it hits 2 pi, and then it starts behaving as a sine function.